Welcome class 12th. Today we will deal with a new chapter, current electricity. In this pandemic time, it's tough to study at home, but we have to. And today's topic is electric current and current density. So first of all, let me define what is electric current. Whenever there is a transfer of charge from one side of an area to the other, we say that there is an electric current through the area. Like this is the area we are taking, and whenever charges are transferring from this side of area to another side, then we say that there is what? Electric current through this area. We can define current as I is equal to delta Q upon delta T, or if we are limiting time as limit delta T tends to 0, delta Q by delta T, then it becomes what? dQ by dt. This is the definition of I in class 12th. And another term is required here, that is current density. So first of all, let us define electric current once again. That electric current through an area is the rate of transfer of charge from one side of the area to the other. SI unit of current is ampere, and we can define ampere as 1 coulomb of charge crosses an area in 1 second, then current is 1 ampere. You can pause the video and you can write the definitions. If 1 coulomb of charge, that is delta Q is 1, passes through or crosses an area in 1 second, then current is said to be what? 1 ampere. Now another term is current density, electric current density. So to define the current density at a point P, like we are considering this as point P, we draw a small area delta S, okay, through P perpendicular to the flow of charge. Means we have studied area vector in flux when we are studying electric flux. Here also the same thing. The current which is flowing to the area, that is only considered in the current density. So if area vector is at an angle theta, then area vector also become at an angle theta. If that area vector is at an angle theta, then area vector becomes the same angle. So what is the current passing through it? Then delta I is what? Delta I is what in terms of current density? See, now the area vector is along this line which is lying at an angle of theta, like area vector is like this. So surface is like this, then area vector will be theta angle. So first of all, define current density. The current density is defined as current flowing per unit area, vector J. Okay, then delta I is equal to what? J delta S cos theta. That's why current here it is shown as scalar quantity, J dot delta S. Both are vector quantities and we are taking dot product. But current is actually not a scalar quantity, it is a tensor quantity. In other video I will tell you what is tensor quantity. Okay, so two terms we have defined, one current and another is current density. Current density is current per unit area, and current is what? Charge per unit time. SI unit of current density will become what? Ampere per meter square. Okay, SI unit of current is ampere per meter square. Okay, so this is the basics of electric current and current density. Now we are going to study Ohm's law in vector form for a conductor. Okay, why Ohm's law? Because whenever current is flowing, some hindrance, some obstruction is offered. Okay, like here, see, I am having a conductor, someone is standing here and charge want to flow from this side. Okay, it is flowing from it, charge is flowing, and this person is binding the charge through a rope. So, and one is pulling from here the charge. So this person who is pulling the charge inside the conductor is who? Voltage. or electric field. This is charge per unit charge upon time. So this is what actually current, and the person who is stopping or checking the charge from going inside is what? Resistance. This is the view of Ohm's law. So voltage V, potential difference applied, is directly proportional to current flowing through the conductor. Okay, a constant is put here, V is equal to IR. This is what? This is Ohm's law, and I want to define what? Ohm's law in vector form. And R is what for a conductor? If its length is L and area is A, then R is proportional to L and inversely proportional to A, and R becomes rho L by A. Let's put the value of R here. V is equal to I rho L upon A. Okay, now put L this side. V upon L is equal to I upon A into rho. V upon L is what? Electric field. I upon A is what? J. So V upon L becomes E, electric field. Okay, and is equal to I upon A is J, current density, just previously we have defined, and rho. Okay, now again put this rho in LHS. These are vector quantities, E and J, current density. So E upon rho is equal to J. What is 1 upon rho? 1 upon rho is conductivity. Okay, rho is resistivity. So J is equal to 1 upon rho becomes sigma E. This is Ohm's law in vector form. See the video once more if you are having any doubts.